الدكتورة منى سفر. الدكتورة منى خدت البكالوريوس والماجستير والدكتوراه من عندنا هنا هو من الشمس. هي دكتورة عندنا قسم كمبيوتر في 2011 والريسيرش بتاعها is more toward pre-configurable computing, application-specific architectures, embedded systems, CAD, verification, and electronic system level design.
زي ما دكتور ماجد presented في التوك بتاعته, at the end of the day we have ECU, electronic control unit, in the car, or a network of electronic control units, and software built on top of it to perform all the functions we talk about, whether infotainment applications or driver assistance application or other functionalities. At the end we have an embedded system, embedded hardware and embedded software. So we will talk in this presentation about the traditional embedded system development flow and why it doesn't no longer cope with such applications and such embedded systems like in the automotive industry. And then we talk about virtual platform. What is virtual platform? What are the advantages of virtual platform? And what are the driving standards and how we can create virtual platforms for different system on chip. We will then talk about virtual platforms for automotive, and then we'll give some highlights for research direction in this domain. So the traditional development flow for embedded systems starts with the specification, and then the hardware development for the system on chip, and then the manufacturing stage, and then the software development start, the integration and the validation. The main problem with this flow is the late software and hardware integration, which causes a lot of problems. We have late feedback from the software developers to hardware to ask them to enhance some unit, or if there is some problem with the system on chip design itself. We have a high penalty of bugs due to ambiguous specification. What if the hardware doesn't meet the real goals for the software to be developed for this system on chip? The penalty will be large if we wait for the whole hardware development flow to complete before we start the software development stage. Having a hardware prototype is no longer valid. It doesn't scale with today's increasing complexity of embedded system. Moreover, it is time and money consuming. And even if you have hardware prototype, you cannot hand it to all the software developers in your team, having a big team to work in the industry. So it's not feasible to have hardware prototypes. Virtual prototypes provide a virtual system which behave exactly for the operating system and for the application software exactly like the real system. So what is virtual platform? Virtual platform actually is an executable software for the complete real system, including the processor core or multiple processor core, and the interrupt control unit, timer, analog to digital converter, CAN, controller, display controller, whatever you have in the system on chip. Okay, you have all this in software models that you can execute just directly in your PC, without any hardware and without any connection to hardware board, and you execute the same binary as on the target board. You execute just the same binary, or else there will be no meaning for the virtual platform. It has to be identical and give you an identical behavior to the real system. You will use the same tool chain, the same cross-compiler and debugger that you will use for the real hardware in order to develop your system using virtual platform. So with virtual platform, actually you can start parallel hardware and software development. So at the same time, the system on chip is being designed, RTL blocks are being implemented, and it is being manufactured. At the same time, the software development can be carried on. The board support package is implemented, the kernels, the drivers, operating system drivers, the applications, and you can start integration and testing through the whole development process from the early start of the hardware, which which actually provide confidence more in the development process. You can refine and test the implementation of the specification and avoid any ambiguous interpretation for the specification at the early stage of the embedded system design. It's available for everyone in a large software development team. Everyone only will need his PC or laptop and the virtual platform on it, and he can run the target software. It gives you superior debug control and flexibility. You can insert breakpoints not only in the software, but in the virtual platform, in the software components for the hardware devices at the same time, so you can be debugging both the software and hardware in parallel, so it gives you a greater visibility for the overall embedded system. It can also help in design space exploration and trade-off analysis. What if you still didn't determine how much core are needed, whether you need DMA, direct memory access controller with 2 channels, 8 channels, will you need more CAN controllers, or one CAN controller is enough? So you can explore this using virtual platform easily and determine what is best for your target application. It also leads to faster time to market, because with this flow, software development, integration, and validation start early before the SoC hardware development completes, which lead to gain time to market, which is actually needed, highly needed in the industry. So what are the driving standards behind virtual platform? The 2 main driving standards behind virtual platform are System C and transaction level modeling. System C is a C++ library from Open System Initiative. It's a library of C++ classes. It's a library of C++ classes, header files, and the simulation kernel. So it adds on, it built on over the C. What it does provide that doesn't exist in the C, it provides processes for concurrency. It provides clocks, which is needed to implement a hardware model using C. So we will need such constructs for clock. Hardware data types like bit vectors for valued logic, because if you go on and use ordinary data types in C, integer, float, and double, they are not enough to model registers, for example, in hardware models which need bit vector values. Weighting and watching and sensitivity for reactivity. How can I model with C++ a model that is tended to behave like hardware and react to events? Modules, ports, and signals. So all these structures are added on top of C++ in what is called System C, in order to help you model your hardware model using a System C language. TLM standard, it's a methodology based on System C that provides interoperability and reuse at transaction level. So at the end, we want to build a system that provides the same behavior as the hardware. What I care about is the read and write access I do to the hardware. I get the same action I want. So I don't really care at that level that when I'm programming a register, I'm raising the read signal, I'm raising the clock, I'm raising the read enabled signal, I'm writing the exact address on the bus. I don't really care about the real processes on the bus signals. All I care about is I'm doing read from a register value, or I'm doing a write to a register value, and I'm waiting that the same behavior as in the hardware will occur. If I'm reading the register now and it should contain 0, I should read back 0. If I'm writing the register value to a specific value, it should be written to this value. So transaction level does not care about signals and abstract all this signal interaction to read and write transaction, between the initiator model, which is mostly the CPU or the processor we have, DMA processor, DSP processor, and the target or slave device, whether it is a memory or any other slave preference. Using System C and TLM, one can implement a whole system, a whole virtual system with CPUs, with timers, with memory control unit, with analog to digital converter, with scan controller, with display controller, and then start to build the software image using the cross compiler he will use to target the real hardware. He will use the same tool chain to build his software image. He can run a complete software stack, operating system, drivers, the same that he will exactly run on the hardware. So actually, a virtual platform-based software development environment provides for you an environment where you can build your system using high-level language such as System C, and where you abstract your models using transaction-level modeling or any other similar technique where you don't care about the details of buses and the interaction on buses in the hardware. You build your software modules that will react to the software in the same way that the hardware will react to the software, the real hardware will react to the virtual software you are building. We have a lot of commercial VB tools in the industry. We have ARM fixed virtual platforms. We have Cadence virtual system platform. We have SoC Designer Plus from Carbon Design Systems, Vista Architect from Mentor Graphics, Virtualizer from Synopsys, CMEX from Wind River Intel, and VLab from VLab Ports. Even big companies in the CAD domain are now oriented to work in virtual platforms and providing virtual platforms. What differentiates one of these providers from the other is the library of virtual models and the library of virtual system on chip it contains. So mainly the majority of these companies are doing partnership with companies like Freescale, Renesas, Altera, Xilinx, in order to have models, to have virtual models, to build virtual models and build virtual system for the real Xilinx board or Altera board or Freescale board, to have a virtual platform for it in their tools, so that they can sell these tools and for users to be able to go for these virtual platforms instead of buying the real chip from the manufacturer and try his software on it. Not only does virtual platform help on the system level integration and on testing a complete system on chip, but it can also help in testing individual IPs. What if I have an RTL, I started to develop the RTL of an individual IP, I can put it into, in a verification environment where the virtual model acts as a golden model and the RTL model is the model under test, and then I start to drive both models with the test cases, scenarios, and the test bench I want, and then I compare the results between the virtual model and the RTL model to verify that the RTL model is working correctly. Actually, this methodology is what is used for RTL model verification in environments such as the UVM methodology. Okay, so what is the addition of virtual platforms? The addition here from virtual platform is that it provides for you the virtual model. Instead of writing models from the specification to act as a standard golden model, you already have the virtual model there and can verify the RTL against it. This allows early development of test cases and test bench and presents a golden reference model for the verification when the RTL exists. Moreover, you can integrate, you can make a hybrid prototype between the virtual prototype and prototype on a hardware on FPGA or an emulator. So you can have your RTL model running on an FPGA or an emulator and integrated in the whole system containing the processor instruction set simulator, DMA, UART, and other devices. What enables this methodology to work is a transaction level modeling abstract with which the virtual platform is built, because you can rely on the transactor unit to change from TLM transactions to real RTL signals that can trigger the action on the RTL, on the FPGA, or on the emulator. This is very helpful in testing huge devices such as SATA devices, USB, PCI devices, where it is very hard to make a test bench to test those devices. Instead, you want to integrate them in a whole platform and run operating system on it and run application software on it and test that they are working as desired. So this is virtual platform in general. So what does it do with the automotive? I'm here quoting a sentence from the general manager of vehicle development division at Mazda. He's saying that ECU is the most important device in vehicles. We need virtual prototyping not only to accelerate the ECU development while lowering the cost, but also to ensure that our ECUs are safe and reliable. So even in the automotive industry, virtual platforms are now gaining more and more being popular and more being used in order to develop the ECU, which is a core part of the smart vehicle. What are the challenges in automotive industry which drives the direction to use of virtual platform? According to BMW Group, an estimated 90% of all innovations in the automotive are driven by electronics and software, and the model requirements are changing very frequently. So you need to be able to develop your system quickly in order to be able to meet the market deadlines. Efficient system development is also becoming increasingly difficult. You have requirements of integrated functions for infotainment, for ADAS, for whatever functionalities we have been hearing about through the whole day in this workshop. 60% of the development time, there is no real prototype available. So how can we ensure that the software developed and that the ECU we are targeting will function as desired and will meet the desired goals? So virtual platforms have started software development early before the ECUs or before the network of ECUs are available. It accelerates the development and the software development and enable testing complex drivers. It facilitates the communication across the supply chain. It eases the semiconductor selection and facilitates exploration and cooperation between the OEM and Tier 1 companies. It also allows testing test corner cases with virtual hardware in the loop environment and automating the regression testing. So we have virtual ECU instead of the real ECU, which you can run on your PC, and then you can run the whole AutoSAR software that Dr. Bassem will introduce to us shortly, with the application software, the basic software, the microcontroller abstraction layer, the drivers, all of these running on the virtual ECU. It enables you to inject hardware and software fault in order to test both the ECU at the hardware level and the software targeting the ECU. It gives you visibility and controllability. You can execute instruction in software and see the values of registers and how hardware models behave for this software. Actually, there are a lot of research direction in this domain, especially regarding establishing open modeling standard that guarantees the interoperability of models and tools, because we have different Tier 1 and OEM in in the automotive industry, and every one of them is using his component how to provide a standard way for modeling, and hence provide a standard way for modeling virtual platforms for different virtual ECUs. Provide mechanism for seamless interaction with existing simulation environment containing hydraulic mechanical properties instead of purely electronic virtual platform. Also, another major aspect is ability to measure power consumption, which is critical for embedded systems in general, and especially for automotive embedded systems. How can we measure power while we are abstracting the hardware and we are not talking about real hardware? So we have to envision new technologies for system level power estimation. We said that the virtual platform focus on the functionality and the correct functionality, so that we are delivering the same functionality as the real hardware. But how about the timing accuracy? Actually, research has to be done in how to increase timing accuracy while maintaining the high simulation speed that virtual platforms provide, in order to empower the usage of virtual platforms. Hardware-software simulation and optimization of multi-core is very challenging. How to simulate systems with multiple operating systems. We can have one core running bare metal application and the other running RTOS or running embedded Linux. Detection of bugs in parallel for the software application running. Automation of the design space exploration to enable user to develop the ECUs that meet their goals. So actually, students here or anyone interested to start trying virtual platform and start to build bare metal applications or embedded Linux and see it running really without having a hardware can start doing this today. There are open source providers like Kimio and open virtual platforms where you can just download a number of virtual platforms for Xilinx, for Renesas, for Freescale, for Altera, and start building software for them, bare metal or embedded Linux, and see how virtual platform works. I would like to add a comment that we have been using here in Ain Shams University in the Computer and System Department. We have been using virtual platforms in teaching embedded system. Instead of having these limitations that we cannot afford getting boards for every student, we have started to teach embedded system and embedded system development and drivers and Linux development on virtual platforms. We already did this last year for the 4th year student, and it was a successful course where students not only learn to start doing software for target processor like ARM, like PowerPC. They have wide range of processors and wide range of system on chip available in these virtual platforms, and they can start working on it. And this ends my presentation. Thank you so much.